Hello, in this video we will look at cubic functions. So let's start with defining what a cubic function is. So it's a function in which there is a cubic term, so x to the power of 3. So the general way we can write a cubic function is with f as a function of x, which is ax to the power of 3 plus bx to the power of 2 plus cx plus d, where the coefficient a is different from 0, because if a is equal to 0, then we don't have a cubic function anymore. Maybe we have a quadratic function if b is different to 0. So let's start to have a look at how a cubic function is in the Cartesian plane. How do they look like? So let's start from the easiest case, which is when a is equal to 1, but all the other coefficients are 0. And so the final form of our function is f, which is a function of x, and it is x to the power of 3. So to understand how we can find the shape of the cubic function in the Cartesian plane, we can write a small table where we give some value to x, which is our variable, and we compute the corresponding values of y. So 0 to the power of 3 is 0, so y is 0 in the first case. Then we have 1, and 1 at the power of 3 is 1. 2 at the power of 3 is 8. Minus 1 to the power of 3 is minus 1. Minus 2 to the power of 3 is minus 8. 3 to the power of 3 is 27, which is 3 multiplied by 3 multiplied by 3. And minus 3 to the power of 3 is minus 27. And now we can paint these points in the Cartesian plane. So let's start from the first one, which is the point 0, 0, and it is the origin of the Cartesian plane, where the small orange circle is. Then we have the point 1, 1, which is here. Then we have the point 2, 8. So x equal 2, y equal 8. This point here. Then we have the point minus 1, minus 1, which is here. We have the point minus 2, minus 8, which is here. And the point 3, 27. But yeah, we don't have enough space on the slide because it goes too far away. The y value is too large. Now we can connect these points with a line, and this line will be our cubic function, and is the yellow line here. So this is the form of a cubic function where a is equal to 1 and all the other coefficients are equal to 0. Now let's try to generalize, and so we go into another case. So we start again from the general cubic function. This time a, b, c, d are all different from 0, and we see what are the properties of this function. So in general we have that this function meets the y-axis in one point, which is here with the circle, and this is the intercept of the y-axis. And so a cubic function has one y-intercept. Then we have 3 points where the function meets the x-axis. And in general we can see that cubic functions have from 1 to 3 x-intercepts. Then we have 2 points here where if we draw the tangent it would be parallel to the x-axis. In fact, these 2 points are points where the gradient is equal to 0, and there are a maximum of 2 points where the gradient is equal to 0 in cubic functions. Finally, well, we can also notice another characteristic of this function. If I enlighten this part of the function with the green color, we can see that the curvature of the function in this part of the graph is towards the lower part of the slide, right? So we can say that the curve in this part has a concavity which is down. On this other part, it's the opposite. The curve is looking upwards, so the concavity is up. And so the point where the concavity of the curve changes is also a characteristic of cubic function. So cubic function have one point of inflection, which is the point where the curve changes concavity. So let's look at another case and see if all these properties that we have written here are true. So another cubic function, this time is the yellow line. So we have one y-intercept, which is this point. We have from 1 to 3 x-intercepts. In this case, we have only one, okay? And then we have a maximum of 2 points where the gradient is equal to 0. In this case, we have 1 point where the gradient is equal to 0, which means it has a tangent that is parallel to the x-axis. And then, what is missing? 1 point of inflection. In fact, we have one part of the graph, the green one, which has a concavity up, and one part of the graph that has a concavity down. And the point in the middle that where the concavity changes is the point of inflection. So this was another case where all the properties are also found. Now let's have a look again to the case we have seen before. So we have a general cubic function that has two concavity up, which is the green part, down, sorry, that is the green part, and concavity up, which is the red part. Now we have seen in a video previously that we can compute the derivative of the function f, and which is generally called first derivative. But if we compute the derivative of the function f, then we are computing the second derivative of the function f. And now we will see how the first and the second derivative are related to cubic functions. So we have already seen that a cubic function has a point where the gradient is equal to 0. This is called a stationary point, a point where the gradient is equal to 0, and so it means that the first derivative of the function f computed in that stationary point is equal to 0. Now let's take a point that is located where the curve is green. This point is a point where the curve is concave down, and if I compute the second derivative of the function f in this point, I will find a negative value. If I take a point where the curve is concave up, what I will find, if I compute the second derivative of the function in this point, I will find it is positive. So in general, all the parts of the function, of all the points of the function where the function has a down concavity have a second derivative that is negative, while all the points where the function has a up concavity, then the second derivative in these points will be positive. In the point we called